Welcome everybody to this week's Green Bank Observatory Community Zoom. Just a few notes about what's happening at the observatory. One thing I'm particularly happy about is the team has tracked down a problem with the subreflector motor controller that was causing some pointing jitter. And that problem is now solved. It turned out to be a bad controller. We swapped that out, and our pointing jitter problems have now vanished. So kudos to a lot of folks who spent a lot of hours working hard on that problem and sorting it out and resolving it. We're getting a lot of, we're excited about the AAS, and we're working hard to prepare for that. Green Bank will feature prominently at the AAS. There's something like 39 papers and posters that have Green Bank data in it. And there is a special session on the future of Green Bank. So if you are in Seattle, please make sure that you attend that. Stop by our booth. We have the best swag of any of the booths, and we will have a survey there. And those who partake in the survey will get extra swag. So please stop by and visit and say hi at Seattle. We're looking forward to that quite a bit. One other thing of notice, stay tuned. This will be coming out in a couple weeks, but we are going to issue a flash call or a special call for proposals for low frequency proposals, particularly large programs that at low frequencies. That will be coming out in a couple weeks, and there'll be an opportunity to acquire some extra time to do low frequency work on large programs. So stay tuned for details. We'll be sending that out by email for our using our normal email channels. All right, that's all I have. So I'll hand it off to Jay Lockman, who will introduce today's speaker. Take it away, Jay.
Thanks, Jim. Today's speaker is Jane Greaves from Cardiff University, and she'll be speaking about GBT photometry, seeking pebbles in protoplanetary disks. And let me just remind everyone that this webinar is being recorded, and you will be able to view it shortly after it ends. And also, if you have questions, please use the Q&A button in the lower right of your screen to submit them, and we'll deal with those at the end of the talk. Okay, Jane, take it away.
Great, thanks very much. I hope you can all hear me okay.
Yes.
Nice great, good to be speaking to a Green Bank audience. So these are GBT data we took some time ago, but myself and Brian published in the last few months. And what we were looking for, and we were really ahead of the game here, is to look for whether there is dust grain growth in protoplanetary disks around young stars. As shown in the sketch there. Excuse me while I just try and rearrange my own screen so I can see my slide. Okay, so at some points in the cross-section through the disk, probably in the midplane, we expect the dust grains to clump together and make larger particles, centimetre size, metre size, etc., and then perhaps all the way up to planets. And so the observational signature of this, which is really nice, comes from radio waves, which can get out of all that dust and gas from the midplane where the action is. And the key thing is that a dust grain emits poorly at wavelengths larger than about its own circumference. So if you get a spectral energy distribution looks a bit like this and suddenly drops down, you've got an idea of how fast how far the grain growth has got from where that kind of knee-shaped position is. And so if we're looking for centimetre-sized particles, we need some kind of centimetre observations. And the opportunity we took with Greenbank, because this hadn't been done before with a large telescope, and so we had no idea well, there was scope for a survey to see what we could discover, whether there are systems with these really quite sort of marble-sized dust grains rocketing about in them. Okay, so we tried to do a very complete survey. So we took a complete list down to a 1 millimetre flux cutoff with no preconceptions, just trying to do all the disks that fell into this kind of class 2 protostar or pre-main sequence star rather category in the Taurus and Ophiuchus regions, and just to see what we got. The survey power, I think, was really impressive. We did 2 pretty short runs, one on each region, just did a few minutes on each, but got down to certainly what at the time was a really impressive depth for this radio photometry. So do the normal scans of the source and then see what signal comes out. So we lost good observing conditions at the end. So on the right, it's an example of one where the data went kind of crazy. So we lost 5 of the targets because the fluxes we measured, which we did publish, but they're not very secure or very sensitive. So we were about 80% successful with the survey aims of this really pioneering survey that we did. So the idea is in the diagram at the top left, is perhaps you've got a mixture of free emission from the system, and you've got a dust spectrum, and you could describe those with kind of 2 amplitudes and 2 slopes, and you've got 4 subbands with the Ka band instrument. So you can do a nice solution and work out what the spectrum of the dust is. And the thing that took us so long to publish is it turned out there's anomalous microwave emission as well in some of these disks, which was completely unsuspected, but there are signatures of spinning nanoparticles in the disks, which is great and really interesting, but kind of messed things up for ages. So you get the kind of composite spectrum I've sketched in, and you get, even if you try and use like the least contaminated points, it's having some effect on the slope for what you infer for the dust contribution. So we got some auxiliary, completely unsuspected science out of that, which was published in 2018 with Greenbank team members. So that's the red diamond dust points. The spectrum pretty clearly goes on up and then drops suddenly in the highest frequency subband, and that's not at all like dust or free behavior. And so that became the archetype of this very small class of now 3 disks with a confirmed anomalous microwave emission signature from spinning nanoparticles. And in the paper, we really dug into this, and we even had a really good candidate that these particles are nanodiamonds, which has kind of opened up a whole area of science. We did some really fun things there. I think we have the only ever observed, and certainly the only published 4 millimetre data point, thanks to Greenbank, that was really important for confirming the spectrum of one of the sources. So having broken new ground there, we went back and tried to look at what the actual survey data was telling us. And I think there are probably 8 other objects, so about a third of our sample, that also have spinning nanoparticles. So they're not very significant individually, but if you average the 8 that look like that kind of shaped spectrum into the yellow dots, you get something that's very similar to the red diamonds. I think at least a lot of those are probably faint spinning nanoparticle candidates, which is something it would be great to follow up with longer observations. And probably also T-tau, which has some of the same behavior and is an individual very bright system dominated by free emission. And clearly none of those are like a simple free spectrum or a dust-like spectrum. Okay, so lots of bonus science. What we were trying to do was construct a spectral energy distribution and fit that and get the dust properties out. So here's 2 of the well-behaved systems we were left with. The one on the left is a very dusty, quite young, actually a binary star system, and the one on the right is a more standard pre-main sequence star. So throwing together all the information available from lower frequencies up to millimeter frequencies, and picking the ones that don't have a lot of anomalous microwave emission, it is possible to get a fairly good fit. So it's a bit jagged because it just goes kind of point to point through all the available data. And of course, this has been taken over quite a lot of time, and the free emission from sources near the star is quite likely to be time variable, but we did our best with that and got sensible looking fits. And these two are actually slightly different. So where it says the Q parameter is just a population index of the sizes, relative proportions of particles of different sizes, but A max is the largest grain size we can say is there. And if you change that, that changes the fit to the data in the way I did in the sketch right at the beginning. So the fits are not perfect with very disparate data from different telescopes, but we did manage to get out our best guesses of how big the grains have grown. So on the left, that's 10 millimeters, 1 centimeter radius grains. And on the right, they're only 1 millimeter radius grains, okay? And so although we would be able to see the signature of 1 centimeter grains with the data, it's not there. So what we were trying to do with the survey is say, what is the effect if you add up all this solid mass on the inferred mass of the whole disk? So the blue ones here are kind of the starting point that existed. This is the around 1 millimeter fluxes turned into disk masses. So that's the distribution you'd think is there if you have no true radio data. There is some patchy data at 3 millimeters because it wasn't so completely surveyed. That's shown by the orange bars, and then the black, white, and grey ones are the results from the Green Bank data going out to the 1 centimeter band. So we weren't managing to deduce dust masses for all of them because of the effects I've talked about. A fewer upper limits, a fewer affected by the anomalous microwave emission, and then the solid black ones, we have a really good idea of the dust mass. So overall, I think we can say that having the benefit of the radio wavelength, the centimeter regime data, it looks like the distribution of masses is somewhat flatter. It doesn't go down in the black bars as prominently it does in the blue bars in these fairly complete surveys. So the conclusions from what we did, we had a set of disks in a flux limited collection, some of which were below a minimum mass solar nebula. The problem we were trying to tackle is why do stars make planets so copiously, given that the disk masses don't appear to be very substantial. And you certainly couldn't make the sun's suite of planets with most of the extrasolar disks we observe. So the general conclusion from that plot I just showed you is that we're boosting the masses of the disks by doing a better census of the large particles that are there. So even though their radio emission is faint, it's very important. So the overall mass budget may tend to be increased by accounting for these larger particles that we can detect. Okay. And although this was quite a small survey, it sets very interesting grounds for the future. So it's very complementary to radio imaging studies, which have now been done very successfully with the VLA, for example. But to really get the great images, of course, you tend to rather cherry pick the most centimeter bright disks. So what we've done in a more complementary way is to have a less biased starting point of which disks we're going to look at. I think the most surprising result is we kind of imagine that grain growth is kind of a non-stoppable process and you somehow end up with a very large grain in the form of a planet. And that's not what we found. In spite of some gaps in the data, we can say that we really didn't see marble or pebble-sized grains in all the disks where we could have, and particularly ones as large as about 1 centimeter in radius. There are actually only 6 of those. Not the 25 where we had the original good data. So can't really say there are any strong trends in that set because there's only 6. It's noticeable that we didn't find any particularly luminous massive young star with large grains. I don't know what to make of that. And also, I think 5 of the 6 systems are single star systems, and that's anomalously single compared to the number of stars that are single in the Taurus and Ophiuchus regions. So possibly there are some factors to do with radiation or gravitational dynamics that affect the formation of large grains, but we need to know a lot more about it to draw any further conclusions on there. So what has come through this work and other work by others, with Alma, for example, is the idea that you don't get a complete picture at any one time, perhaps. So perhaps the growth through centimetre-sized grains to much larger bodies is a small fraction of the total disk lifetime. So you're just getting a snapshot of the ones doing it at that particular time. Or possibly that a disk that looks millimetre bright has millimetre-sized grains everywhere, but the grains that successfully form the larger and larger bodies are only in certain regions. And that's why we don't detect all the disks as centimetre bright. So this has really been groundbreaking for setting the scene for new surveys. So I'm the PI of one called Pebbles, which is Planet Earth Building Blocks, a legacy E-Merlin survey, because E-Merlin's network of telescopes gives us enough resolution to actually distinguish the 1AU zone where an Earth might be forming from, say, where Jupiter or Saturn analogues would be forming. So that's building up. We have a lot of data from that, and are hoping really to set the scene again for larger scale works, so with next generation VLA or with SKA. So the one you're looking at there is a genuine disk image. It's our pioneering disk image from Pebbles, and we're really starting to get some insights through radio observations of how planet formation happens, is my final conclusion. So thank you.
Thanks very much. It's a very fascinating result. Please submit questions using the Q&A box in the lower right of your screen. And let me start by going back to anomalous dust emission. Is there anything in the characteristics of the system that lets you predict when you will see that?
No. So we've only found it so far really securely for individual stars, for luminous, like Herbig type stars, but certainly not all of those. They can look very similar. The disks can look very similar. And we only found this 3, which show the anomalous microwave emission. And they turned out to be 3 in which nanodiamonds are known, which is extremely rare. This is found from infrared spectra. So where you find things like PAH features pretty much universally, there are like literally 3 that have nanodiamond signatures, and they were the 3 that had the AME as well. So no idea what's going on there, but it was a fascinating thing to do.
Yes, that is. Okay, we have a question here. Could it be that there's a very rapid aggregation period for gravitational growth of sizes greater than 1 centimeter into larger bodies, so their population disappears in a very short time?
Yeah, I think that's coming to be the opinion of the community. So not necessarily gravitational, but there are simulations that show you can get kind of pressure conditions in disks where larger particles kind of stop and hang about. And so then if you've got like a pebble swarm, then there would be enough that the timescales for those to aggregate onto each other would be much reduced. You can get a zone which you can get like a planetary core mass object pretty quickly, yes.
Mm-hmm. So another question, do you assume a dust size distribution like r to the minus 3.5?
Yes, so that was the equivalent of Q, which is another population index in the spectral energy distributions. So we didn't assume it, but we used some papers that gave a prediction for what the ACD would be like for different R minus 3.5, R minus 2.5, whatever, and tried basically fitting all the permutations of those till we got the best one of the data. So it's not an assumption, and I think we got a fairly flat population index was required. I'm sorry, I forget. The details are in the paper.
Mm-hmm. Okay, thanks. Another question, do you see variations in the peak wavelength of the AME?
Yes, kind of. So in the three systems where we spent a lot of time getting multi-wavelength data, the most luminous one, the AME peak, was really high. Actually, unfortunately, at a band where we didn't have data, probably something like around 60 gigahertz or something. So we have a sample of 3, of which 2 are quite similar, and the really massive luminous star appeared to have its AME at a higher frequency, which kind of fitted with the AME theory. But yeah, I would love to do more on that, because with 3 objects, we didn't really get too deep into it.
Mm-hmm. Are the pebbles made of rock, ice, carbon?
So in the models we were using, they're a kind of amalgam of the materials we expect to be in protoplanetary disks. So we're probably looking at fairly far out from the star, so you would expect there to be some ice content. I think the fitting didn't depend terribly much on that, but we used a kind of protoplanetary mixture rather than an interstellar mixture. Yeah.
Mm-hmm. How can we distinguish if we are detecting large grains or evidence of photoevaporation in the centimetre?
Yes, so we've looked at this more in the context of Pebbles, where we're getting images. So it was raised that if you get like kind of elongated structure, it could be photoevaporative wind off the disk. So we used some models of this again, which I think mentioned, or at least mentioned in the paper we have coming out, which my postdoc Katie Hesterly is leading. And the models for the driving at the photoevaporative wind from the disk indicate that the flux would be there, but it would be even smaller than something we can detect with eMerlin. So even though it might be disk shaped, it will be too faint to detect. So what we're imaging should be the actual representation of the dust emission from the disk.
It's another question. The Rossby waves concentrate the pebbles. Won't those and then puddles go optically thick and hence be invisible? Yeah,
so this is an advantage of the radio stuff, is that the concentrations, I mean, an enormous concentration of pebbles, I think, would go optically thick. But I'm not sure at what sort of density that would happen. But we should, I think, still be seeing sort of the most opaque spots in the disk if we were imaging, or the most opaque region if we're doing photometry. And I think a lot of people doing disks haven't quite appreciated yet. You can get the beautiful disk images with ALMA, but most of the ALMA wavelengths, the dust will be optically thick through pretty much the entire disk. So even at 3 millimeters, the disk is an opaque object for something that's kind of massive enough to image in detail. So it's kind of 7 millimeters and longer is a really good sweet spot for getting true mid-plane disk structure.
And another question. Since these observations are unresolved, parentheses, so it's an average of the disk, could there still be large grains and just their signatures being lost in the average?
Yes. So if you had, for example, pebbles forming in a narrow ring somewhere, that would be really hard to see with data in the depth we've got. Yes, so that's true. That's very true. And this is where the photometry and the imaging are really complementary. So, you know, a further deeper green bank photometry survey, for example, could set the scene of interesting candidates, which could then be done with something like VLA to see where the structure is. And the disks at EVLA survey, which I was also part of, led by Claire Chandler, has an enormous wealth of that sort of 1 centimetre band data. So that, again, very complementary. I think some of that is not yet published for reasons having enough people to work on it, but there's some beautiful data in there.
Mm-hmm. And there was an auxiliary question. Did you include scattering in the AMAX calculations?
I think it wasn't necessary. I think it was probably, well, I think it was probably included in the models that we use. So we didn't run our own models for that, but I think it's included in the calculations. But I think for the very large particle sizes, it's not particularly relevant.
Okay, thank you. Well, that concludes the questions. And let me just say that since the GBT observations and future GBT observations were mentioned several times during your presentation, we have a proposal deadline coming up in early February, which is under 2 months away. And so we'll be open for consideration of this kind of science at that time. Before signing off, let me remind everyone that this session has been recorded, and so you can view it. Just go to our website, greenbankobservatory.org, and look under science, and you will see the link to this session and as well as others. And next month, sorry, 2 weeks from now, we will have the next talk in this series. Antoine Marshall of the Australian National University will be speaking on mapping the thermal condensation of diffuse H1 in the North Celestial Pole loop with the GBT. We look forward to seeing you then. Thanks and goodbye.